equals 10x1 plus 5x2, subject to two constraints. So first of all, based on our requirements for a standard maximization problem, are they all met? Is the objective function maximized? Have we maximized the objective function? Right here, does it say maximize P?
Yes.
Yes. Do we have non-negativity constraints?
Yes.
Yes. And are all of our constraints less than or equal to?
Yes.
Yes. So we've met the three requirements for a standard maximization problem. So we can continue on to use the simplex method. The first step is to rewrite all of the problem without inequalities. We start with the constraint. So we have 4x1 plus x2, and this is our first constraint. So we have to add a slack variable of u. And that changes the less than or equal to 28 into equals 28. Okay? Second inequality, we have to add a v to change the less than or equal to 24 into an equals 24. And then we always write the objective function representation in the bottom row of our initial system. And recall, we need to move all of the variables to the left-hand side. And when we subtract 10x1 and 5x2 on the right, we're left with just 0. And if you'll notice when I wrote this initial system, I've lined up all my x1s, all my x2s. The only u gets its own column, the only v gets its own column, and p gets its own column as well. And I space it out like that when I write it to make sure that when I create my initial simplex tableau that I'm not missing anything, that I filled in all of the places, spaces, entries. Are we good so far? All right. So then from this initial system of equations, we need to create a tableau. Can anybody tell me what the first row should be?
4,
4,
1,
1, 1,
0,
0, 0, 28. Right. And then the second row, and I'll show it to you in a minute. 2, 3, 0, 1, 0, 24, yep. And then the last row?
-10, -5, 0, 0, 1.
Good.
0.
Very good. Okay, so right here is our initial simplex tableau. I'll give you a minute to write that down, if you haven't already. So the first step in selecting the pivot element is to find the most negative entry in the bottom row. What's the most negative entry in the bottom row? Negative 10. So this negative 10 identifies column 1 as my pivot column. Okay, I know I'm going to be pivoting somewhere in column 1. And then to determine the pivot row, I need to divide the right-hand side values by the values in the pivot column. So 28 divided by 4 gives me 7, and 24 divided by 2 gives me 12. And I need to select the smallest of the two quotients, the smallest of the non-negative quotients. And obviously 7 is the smallest. So that identifies column 1, row 1, as the position of the pivot element. Okay, most negative in the bottom row gives me my pivot column, and the smallest quotient of the right-hand side values with the values in that column identifies the pivot row. So you should use the pivot program that you have on your calculator to pivot about row 1, column 1 in this. What size matrix would this be if we put it in? How many rows? By how many columns?
5.
Okay, so if you want to take a minute and put that into your calculator. It's a 3x6 matrix. And once you get it in, run your pivot program about row 1, column 1. And I'm just going to talk in the meantime as you're typing that. What my notes are showing here are the row operations required to change the 4 into a 1, and then the other values in that column into zeros. So go ahead and keep typing in your matrix and run your pivot program on row 1, column 1, and do not exit the pivot program. Okay, so the row operations required to change this 4 into a 1 would be times row. We would have to multiply this entire row by 1/4. So 1/4 times 4 gives me 1. 1/4 times 1 gives me 1/4 or 0.25 both times. Anything times 0 is 0, and 1/4 of 28 is 7. So that dealt with the first row, and I left everything else the same. So I'm still pivoting about this row 1, column 1, but it's going to require 2 more row operations to make the 2 into a 0 and the -10 into a 0. And I put those together in 1. So when I need to change a number into a 0, I ask myself, what's the opposite of this number? It's -2. So I'll multiply -2 times row 1 and add that product to row 2, and that's represented by this row operation here, row 2 minus 2, row 1. And to change this -10 into a 0, I say, what's the opposite of 10? Excuse me, of -10, it's 10. So I multiply 10 by row 1 and add that product to the row 3 values. And you can see, after doing those 3 total row operations, I've successfully pivoted about the first row and first column. So when you ran your pivot program, did you get a matrix that looked like this?
Yes.
Yes, but you probably have fractions in it, right? The reason why I didn't put fractions is because they don't type so pretty when you insert one of these in a Word document. So you should have the same thing as I have here. And that's why I told you don't write everything, because you're not performing these row operations because you have the RMU pivot program. But before that was made available, we had to do it old school by hand. So now that we've successfully pivoted, we need to examine the bottom row. Are there any negatives left in the bottom row? Yes, there is only 1. So that means we're not done yet. We have not reached our optimal solution. So let me scoot this up a little bit. So since there is only 1 negative number in the bottom row, that identifies our pivot column as column 2. And now, how do we decide which is the pivot row?
You still do want the negative in it, or no?
You have to deal with that column, but do you remember what you
The
had
lowest.
to? The lowest,
Value in the column, the lowest constraint, or, I don't know.
the lowest quotient.
Yeah.
So that means we have to take the right-hand side value and divide it with the value in the pivot column. So 7 divided by 0.25 is at 28, and 10 divided by 2.5, which should be 4. So of those 2 quotients, the smallest is 4. So that identifies the pivot row as row 2. So I think you press enter or execute to continue your pivot program on your calculator. And this time you're going to tell it row 2, column 2, or column 2, row 2, depending on which way your calculator asks for it. And again, I've written out the 3 row operations that would be required to change the 2.5 here, which is our pivot element, into a 1, and the rest of the values into that column, into zeros. So I'm going to scroll down just a little bit more so that you can see what you should get as a result of pivoting about row 2, column 2. When you do that in your calculators, do you get this tableau or matrix? Yes, fantastic. So are there any negatives in the bottom row? No, that means we have reached the optimal solution. So now we have to define what is the optimal solution. And to do this, I'm going to label my columns. We had x1, x2, u, v, p, and our constants on the right-hand side. So what we need to do is we need to look for unit columns. A unit column is defined by a column that contains 1, 1, and everything else in that column are zeros. So is x1 a unit column? Is there a 1 in it?
Yes.
And all the other values are zeros?
Yes.
So then x1 is a unit column. So what we have to do to identify the solution is take the 1 in that column and we want to connect it to the value on the right-hand side. So that's how I get x1 is equal to 6. Okay, now is x2 a unit column? Yes, because there's 1, 1 and the rest are zeros. So we take the 1 in this row and we connect it with the constant on the right-hand side, and that's how we get that x2 is equal to 4. Now is u a unit column?
No.
No. Whenever I have columns that are not unit columns, that variable is equal to 0. So, since this is not a unit column, u is equal to 0. Is v a unit column?
No.
No. So v is equal to 0. And then finally, is p a unit column?
Yes.
Yes. So we take the 1 in that row and connect it to the constant on the right-hand side. We get p is a maximum of 80 when x1 is 6 and x2 is 4, and both of our slack variables are 0.